Good morning, students. Today we are going to discuss about Faraday's law and Lenz's law, okay, and example problems. Okay, students, clear? Right. Start with Faraday's laws. Okay. In last class we discussed Faraday's law, but again I'm starting with Faraday's law. Okay, students. Right. So Faraday's law. Yes, there are two laws. Faraday's first law is nothing but whenever magnetic flux, what is magnetic flux? That is pi. Okay, whenever magnetic flux linked with the closed circuit changes, an EMF is induced in the circuit, right? Pi, yes, pi b. Please remember magnetic flux is pi b. So first law gives that magnetic flux changes in a circuit, EMF is induced in the circuit. Yes, right? Now come to the second law. The second law is nothing but the magnitude of EMF in a closed circuit, right, is equal to the time rate of change of magnetic flux linked with the circuit. Okay, the magnitude of the EMF in a closed circuit is equal to the time, yes, rate of change of magnetic flux linked with the circuit. Okay, okay, students. So this is the second law. Okay, Faraday's second law. So therefore, the formula for second law is psi, which is equal to d pi by dt. D pi by b by dt. D pi is nothing but magnitude of rate of change of flux, d pi by dt. Okay, students, the two laws are very important. 2-mark question. Okay, right. Just again, for your understanding purpose, Faraday's laws of induction. See this: the induced EMF in a wire loop is proportional to the rate of change of magnetic flux through the loop. So the magnetic flux is pi b, which is equal to BA. That means BA cos theta. So cos theta is nothing but 90 degrees. So therefore 1, therefore B into A, right? The unit of magnetic fluxes, again I'm telling, Weber. 1 Weber is equal to 1 Tesla meter square. Okay, students. So here, for understanding purpose, this is pi b. Pi b is nothing but magnetic flux, right? Okay. Now in that yes, second law, no, based on the second law, induced EMF, right? See the formula: EMF is equal to minus d pi by dt. This d pi by dt is nothing but rate of change of magnetic flux. Okay, right? So this equation may be expressed in another way: pi 2 minus pi 1. What is pi 2 minus pi 1? That is, pi 2 is nothing but final flux and this is the initial flux. That's why rate of change of magnetic flux. Okay, change in magnetic flux with respect to time. That's why d pi by dt is, and elaborately write, pi 2 minus pi 1 divided by t. Okay, right? Suppose if that suppose we are consider coil, the coil has n number of turns. What is the EMF? Suppose if the coil having n number of turns, the EMF E is equal to minus n d pi by dt, and minus n pi 2 minus pi 1 by dt, rate of change of flux, which produce induced EMF, right? So based on the current, yes, this is EMF. So then the current, induced current, what is current? I is equal to d pi by, what is, that is 1 by r into t. No, that's why minus d pi into r. R is the resistance. So therefore for the induced current d pi divided by r into dt. Yes, for charge, what is charge? The current is nothing but dq by dt, right? Rate of flow of charges. Therefore, dq divided by dt into I, is equal to I. Therefore, I am substituting I formula here. D pi divided by r into dt. So, what is? Yes, cancel. dt cancel. Therefore, I can get dq is equal to minus d pi by r. Okay. Yes, this is for your understanding purpose, right? So please note it down. 1 marks will come from this area. Okay, and see the note. Induced EMF does not depends on resistance of the circuit, whereas the induced current and the induced charge depends on resistance. Induced EMF does not depend on resistance of the circuit. Okay, and where the induced current and induced charge only depends on resistance, right? Okay, current and charge only depends on resistance. Okay, students, right? Okay, next example problem 4.3, right? Example problem 4.3. Okay, see this. A cylindrical bar magnet is kept along axis of a circular solenoid. A cylindrical bar magnet kept along the axis of a circular solenoid, right? If the magnet is rotated about its axis, okay, and find out whether an electric current is induced in the coil. So we have to find out the is there any electric current in the induced current in the coil. Okay, students. Okay, right. See the solution, because this is theoretical one, there is no data, therefore yes, this solution is enough. Okay, see this. The magnetic field of a cylindrical magnet, the magnetic field of a cylindrical magnet is symmetrical about its axis, as the magnet is rotated along the axis of the solenoid. So there is no induced current in the solenoid, because the flux linked with the solenoid does not change due to the rotation of the magnet. The axis of the solenoid, there is no change due to the rotation of the magnet. Okay, magnet is only rotated, so therefore there is no flux changes. Okay, students, right? Okay, because induced EMF condition is whenever the magnetic flux changes in the closed coil, what will happen? A EMF is induced, right? So in this case, there is no flux changes, due to that there is no which one? Current, induced current in the solenoid. Okay, students, shall we go to next one? Okay, next problem 4.4. Yes, so in this problem some data is given. See this question. A closed coil of 40 turns and of area 200 centimeter square. So turns is given 40 and area 200 centimeter square. Okay, is rotated in a magnetic field of flux density. So the flux density pi is equal to 2 Weber meter power minus 2. It rotates from a position where its plane makes an angle of 30 degree. So theta is equal to 30 degree, right? And with the field to position perpendicular to the field in a time 0.2 second. Therefore time is equal to 0.2 second, and that magnetic field is perpendicular. Okay, so these are the data, right? Okay, now we have to find out magnitude of induced EMF in the coil. Okay, magnitude of induced EMF. Okay, students, right? Now, yes, see the data. N is 40 turns and magnetic field 2 Weber meter power minus 2, area 200 centimeter square, right? That centimeter square is equal to 200 into 10 power minus 4 meter square. Centi means 10 power minus 2, right? So square now, that's why 10 power minus 4. And theta is equal to 30 degree and t is equal to 0.2 seconds. You have to find out EMF, right? Okay, students. Now, please N. So from the magnetic flux formula, pi is equal to BA cos theta. That's why I'm taking here initial flux pi I, which is equal to BA cos theta. So this formula is based on what? Magnetic flux formula. But here I'm taking initial. Yes. Here theta is 30 degrees given, therefore I'm taking that 90 minus 30 degree, because perpendicular no, magnetic field is perpendicular no, that's why 90 degree minus 30 degree I can get 60 degree, right? Therefore see that I'm just substituting the BA values and theta values here. What is B? 2. And what is A? 200 into 10 power minus 4 into cos theta. Theta is 60 degree. Cos 60 is equal to 1 by 2. You see this? 2 into 200, 400 into 10 power minus 4, right? Here 2 and 400 cancel, I can get 200, and 200 into 10 power minus 4, yes, Weber meter. Again I am simplifying, 2 into 10 power minus 2 Weber. So initial flux is 2 into 10 power minus 2 Weber. Okay, the same time final flux, yes, that time the final flux go to that flux changes no, that's why the angle is theta is equal to 0 degree, theta is equal to 0 degree, the same flux formula, but here I'm taking f for final flux, and pi f is equal to BA cos theta. B value is 2 and A value is 200 into 10 power minus 4 into cos 0 degree, yes, cos 0 degree is equal to 1, therefore 400 into 10 power minus 4, 4 into 10 power minus 2 Weber. Yes, this is the final flux. Okay, according to Faraday's laws, changes in flux, right, with respect to time, no. Therefore, I'm going to find out changes in flux. Yes, change in flux is nothing but d pi by d is equal to final flux minus initial flux. Final flux is 4 into 10 power minus 2 and initial flux is minus 2 into 10 power minus 2. Therefore, 4 minus 2, 2. Therefore, 2 into 10 power minus 2 Weber. So, this is the change in flux. Okay, so with the help of this change in flux, we have to find out EMF. See the EMF formula, induced EMF psi, which is equal to N into d pi by dt according to second Faraday's law, rate of change of magnetic flux. Therefore, N is 40 turns because his data is given no. That's why. So N is 40 into change in flux. Change in flux is equal to what? 2 into 10 power minus 2. Here time what? Dt. So dt is what? Time. What is time is given? 0.2 second. Therefore 0.2. See this? 40 into 2, 80 into 10 power minus 2 divided by 0.2. Therefore you will get 400 into 10 power minus 2. Again if you will yes, 10 power minus 2 go to this side. That means 10 power minus 2 to this side, you will get EMF. E is equal to 4 voltage. Yes, EMF is nothing but potential now. That's why V voltage. Okay, students, EMF. Do you understand this one? Okay. The induced EMF is nothing but rate of change of magnetic flux. That's why first we calculated initial and final and change in flux and substitute the induced EMF formula. Okay, students, right? Okay, next example problem 4.5. See this, a straight conducting wire is dropped horizontally from a certain height with its length along east-west direction, will an EMF it induced it? Justify your answer. See again, I'm telling, a straight conductor wire is dropped horizontally from a certain height with its length along east to west. Just imagine. So will an induced EMF produced? Yes. See this? Solution yes. An EMF will be induced in the wire because it moves perpendicular to the horizontal component of earth magnetic field. Earth has magnetic field, no? Yes, from north pole to south pole, right? Due to that EMF induced because the bar, yes, the wire dropped horizontally, right? Horizontally. That's why the earth magnetic field is acting perpendicular to the plane of the wire. Therefore definitely EMF it is induced, because when the moving from east to west direction, what is changes? Magnetic flux changes, because magnetic field present, no earth magnetic field. That's why the induced EMF is produced. Okay students, right. Next topic is Lenz's law. Next topic, Lenz's law. Okay, say this: Faraday's laws give the magnitude and direction of the induced EMF, and therefore the direction of any induced current given by the Lenz's law. The Lenz's law is a simple way to get the direction straight with less effort, right? Okay, therefore the Lenz's law is the induced EMF is directed so that any induced current flow will oppose the changes in magnetic flux. Okay, that means decreasing magnetic field is equal to EMF creates additional magnetic field. If increasing flux, EMF creates opposed magnetic field. So these are the two terms to understanding the Lenz's law. Okay, right? Yes, see the another definition. Simple definition for Lenz's law. Yes, see this: the direction of the induced EMF, the direction of the induced EMF or induced current in such that it opposes the changes that in producing it. This is the simple definition for Lenz's law. So Lenz's law definition is important 2-mark question. Okay students, okay, right. See this: if the current is induced due to motion of the magnet, then the induced current in the coil set itself to stop the motion of the magnet, right? At the same time, if the current is induced due to the changes in current in primary coil, then the induced current is such that it tends to stop the changes. This is explanation for the Lenz's law. Okay, now here also Lenz's law and conservation of energy. See that Lenz's law. According to Lenz's law, the induced EMF opposes the change that produced it. It is this opposition against which we perform mechanical work in causing the change in magnetic flux, right? Therefore, the mechanical energy is converted into electrical energy. So the mechanical energy is converted into electrical energy. So therefore, the Lenz's law is accordance with the law of conservation of energy. Please note it down. This one is very important question. Lenz's law is accordance with the law of conservation of energy. Okay, students, right. Next, see this: if, however, the reverse would happen, then a little change in magnetic flux would produce an induced EMF or induced current, which would help the change of magnetic flux further, thereby producing more current. The increased EMF would then cause further changes of flux, and it would further increase the current also, and soon. So this would create energy out of nothing, which would violate the law of conservation of energy. Okay, so this paragraph for additional work, you don't worry about this one. So up to this, okay, portion. Okay, students, right? Okay, next, Fleming's right hand rule. Okay, Fleming's right hand rule. Okay, so see this, when a conductor moves in a magnetic field, okay, moves in a magnetic field, the direction of motion of the current under the magnetic field and the induced current will be explained by which rule? Fleming's right hand rule. Okay, right? When the conductor moves in a magnetic field, yes, it experiences, yes, what? The force, at the same time some current are induced. So these are explained by Fleming's right hand rule. Okay, students, see this Fleming right hand rule. See this thumb finger, right, and that fourth finger and middle finger. Okay, right. First, this thumb finger represent the direction of force on the conductor, and the fourth finger give the direction of magnetic field. See this north pole and south pole, the magnetic field, and that this middle finger gives the direction of current. Okay, therefore we conclude, yes, sentencely, yes, right hand rule, Fleming's right hand rule is, see this, the thumb, index finger and middle finger of right hand are stretched out of mutually perpendicular directions, right? If the index finger points the direction of magnetic field and thumb finger indicates the direction of motion of conductor, and then the middle finger gives will indicate the direction of induced current. Okay, so this is the definition of Fleming's which rule? Right hand rule. So therefore the index finger gives the direction of magnetic field and thumb finger indicates the direction of motion of conductor, and the middle finger gives the direction of induced current, right? Okay, students, this is Fleming's which rule? Right hand rule. Important 2-mark question. Okay, students, right, is followed by that example problem 4.6. See this question, if the current I flowing in the straight conducting wire, the current flowing I in the straight wire shown in the figure and decreases, current decrease, find out the direction of induced current in the metallic square loop placed near it. So this is one square loop, closed area, that is closed area is nothing but loop, therefore one metallic area placed near this conductor. So find out the direction of induced current. Okay, okay students, there is no data, therefore we have to apply the induced current and induced EMF concept. So see this, from right hand rule, from right hand rule, what is right hand rule? Thumb finger, middle finger and fourth finger mutually perpendicular to each other, and thumb finger gives the direction motion of conductor, and the fourth finger gives the direction of magnetic field, and that the middle finger gives the direction of induced current, right? So please remember that right hand rule. So from that rule, the magnetic field by the straight wire is directed into the plane of the loop perpendicularly. So and its magnetic flux is decreasing, right? The magnetic field is perpendicular to the plane, therefore magnetic flux is decreasing. The decrease in flux is opposed by the current, which current? Induced current in the loop by producing magnetic flux in the same direction. Okay, the wire is perpendicular to the plane of the which one? That loop. Due to that, the induced current producing the magnetic field in the same direction. Therefore, the magnetic field acting inwards, right? And the direction of induced current in the loop is which direction? Clockwise direction. Which direction? Clockwise direction. The wire, the induced current is perpendicular to the plane of the loop. Due to that, yes, the current, induced current flow in which direction? Clockwise direction. See this? The current in this is that perpendicular to this one. Due to that, the current flow in which direction? Clockwise direction. Should be like clockwise like this. No, that's why it started from here to here. Clockwise direction. Okay, students, you have to apply the Lenz law. Lenz law is to oppose that, producing it. That is, which is producing, induced current is producing. Okay, students, right. Next problem, 4.7. The magnetic flux passes perpendicular to the plane of the circuit and is directed into the paper, right? So this diagram, these intos are magnetic flux field, magnetic flux, right? Okay, if the magnetic flux varies with respect to time, yes, that the relation magnetic flux pi b which is equal to 2t cube plus 3t square plus 8t plus 5 meter Weber. What is the magnitude of the induced EMF in the loop when t is equal to 3s? The time is equal to 3s. Find out the direction of the current. So this is that this dots are magnetic flux and it has resistance. This is on closed area. Okay, they have to find out the current, induced current in the circuit. Okay, this is one closed circuit. That yellow lines are indicate that closed circuit. Okay, students, right. See this example problem 4.7. Pi b is equal to, this is a given, 2t cube plus 3t square plus 8t plus 5 meter Weber, and n is equal to 1. The number of turns equal to 1 and the time is 3 seconds. Therefore, according to the Faraday's second law, the induced EMF is equal to rate of change of what? Magnetic flux. Therefore, d pi by dt into n. That's why the n is inverse d n pi by divided by dt. Here what is n value? 1. Therefore 1 into d pi by dt, d pi by dt. Therefore d divided by d into pi b, because pi b is given or not. Therefore see that I'm substituted 2t cube plus 3t square plus 3 8t plus 5 into 10 power minus 3. Milli means 10 power minus 3. Therefore I am doing differentiate with respect to time. Therefore if I am differentiate with respect to time, 2t cube I can get 6t square, 3t square I can get 6t plus 8t with respect to time I can get 8. So this is the constant, therefore this will be cancelled. So finally EMF I can get 6t square plus 6t plus 8 into 10 power minus 2. Yes, at the t is 3 second, therefore I am substituting the t value is equal to 3s, therefore size equal to 6 into t. Sorry, take 6t square, no, therefore 6 into 3 squares are 9 plus 6 into t, 6 into 3 plus 8 into 10 power minus 3, therefore 54, 18 plus 8, therefore I can get 80 into 10 power minus 3 volt. Yes, EMF is equal to 80 into 10 power minus 3 volt, therefore 80 millivolt, because 10 power minus 3 is nothing but milli. Okay, students, right? It is easy now. Okay, motional EMF. Motional EMF. Okay, students, right? So this is a 3-mark question, right? Which question? 3-mark question. See this, motional EMF from Lorentz force, right? From Lorentz force. What is Lorentz force? Right, yes. When the material or anything move in an uniform magnetic field, it experiences a force, right? This is the Lorentz force. Please remember the Lorentz force. When the magnet or when the material or wires moves in an uniform magnetic field, it experiences a force, right? This is the Lorentz force. Now, motional EMF from Lorentz force. Motional EMF. When the object is moving in an uniform magnetic field, induced EMF is produced. That is the motional EMF. Okay, students, it is a 3-mark question. Okay, now come to the theory. Consider a straight conducting rod AB of length L in an uniform magnetic field B, which is directed perpendicular to the plane of the paper. So the magnetic field is acting perpendicular to the plane of that one, and that rod is AB, the length is L. Okay, next, the length of the rod is normal to the magnetic field. At the same time, the rod moves with constant velocity towards right side. So the rod moving in an uniform magnetic field in right side, definitely the rod experience a magnetic Lorentz force. Okay, students, so based on the theory, and see, this is the diagram. See, this into marks are magnetic field. The magnetic field is perpendicular inwards. This is that conducting wire. The length is L. This one is moving right side. Okay, so definitely electric field is present. At the same time, EMF is induced. EMF is induced because of what? This conductor moving in a uniform magnetic field, right? That field is perpendicular to the plane and moving with velocity. So due to that, Lorentz force experiences. Okay, students, right? Is, see this, Lorentz force act on the free electrons in the direction from B to A. When the conducting wire move in a magnetic field, it experiences Lorentz force. Okay, so inside that wire, conducting wire, free electrons present? No, that free electrons in the direction B to A. Therefore, magnetic Lorentz force is FB, which is equal to B for magnetic Lorentz force, is equal to minus E into V into B. V is velocity and B is the magnetic field. This is equation number 1. Okay, now the accumulation of free electrons produced potential difference due to the Lorentz force. Due to the Lorentz force, the electrons are accumulated. That accumulation of free electrons produced potential difference. Produced a potential difference. Okay, students. Therefore, the potential difference is basic formula. V is equal to the ratio of electric field to the magnetic field. From this one, E I am taking V into B. Okay, this is one side. Now, due to the accumulation of free electrons, is electric Coulomb law forces will be created. Yes, that force is equal to Fe is equal to minus E into E, because electric field is present. So what equilibrium conditions? Okay, but equilibrium conditions, both Coulomb force equalized by the which force? Magnetic Lorentz force. That's why in equilibrium the Lorentz force, which is equal to the Coulomb force. Okay, right? Therefore just I'm equal the two forces. Therefore see that FB is equal to FE. Therefore modulation of minus E into V is equal to minus E into E. So here minus E cancel. So here the magnetic field is perpendicular. Therefore VB into sine theta. Yes, VB into sine theta. So why we had sine theta? Because magnetic field is perpendicular. That's why sine theta. Right? Sine 90 degrees equal to 1. Therefore VB is equal to E. VB is equal to E. This is equation number 1. See here sine 90 degrees equal to 1. Okay. The same time the potential difference between two ends. The conductor has free electron. Due to that, what is produced? Potential difference. The potential difference between the two ends, V, which is equal to E into L. V is equal to E into L, right? Electric field into length. Now if this E value substituting from this equation, because E is here now, therefore what is E? V into B. Therefore the potential V, which is equal to velocity into B, velocity into B into L, right? This is equation number 4. Okay students, right? Next, followed by that equation number 4, the Lorentz force on the free electrons is responsible to maintain this potential and produce the EMF. So which is only responsible to produce EMF? Lorentz force. Therefore EMF, according to EMF, psi is equal to BLV. Yes, because this one, the potential is V is equal to VBL, no, the same one, because potential V is nothing but what is equal to EMF, no, the potential and the EMF both are same or no? Yes, therefore the EMF E, which is equal to BLV. V is magnetic field, L is the length, V is the velocity. This is equation number 5, right? And this EMF is produced due to the movement of the rod. The EMF is produced due to the movement of the rod. Yes, because the rod is moving towards right side, no, in uniform magnetic field. So EMF is produced. Due to the EMF, what is produced? Current will be produced. Okay, now see this, the EMF is produced due to the movement of the rod, and it is called motional EMF. So this EMF is called as which EMF? Motional EMF. And when that EMF induced in the wire, definitely will produce the current. Yes, that current is induced current. What is induced current? I. Small I is the induced current. According to Ohm's law, I, which is equal to V by R, I is equal to V by R. Therefore here the induced current, which is equal to what? Yes, induced EMF by resistance. E is equal to potential and divided by R, that format. Therefore I am substituting E value. What is E value? Yes, see this, BLV. Therefore BLV divided by R. This is which one? Induced current. Which current? Induced current. But which is that induced EMF? E is the induced EMF. Okay students, induced EMF. Do you understand? Okay students, right? Okay, have any doubt? Please see the video slowly and take notes. Okay students, okay. Today class is over students. We'll see on next video. Okay, thank you students.